for part C, Quicksort. Part C.6, best case efficiency of Quicksort. All right, so this time we know under what situation we have the best case. After our analysis in C.5, we know it happens at the most balanced partitioning. Yeah. So this time we can assume the best case after one partitioning, we get two subarrays with approximately the same size, approximately 1/2 of the total number of elements. Yeah. So from that, based on that assumption, we can write recurrence relation easily. Okay, yeah. So the base case T of 1, so the number of comparisons, 1 element, 0, right? 2 elements, 1 comparison. Get it sorted. Yeah. The general case T of n, the total number of comparisons for data size n, by our best case partitioning, we need to conquer each subarray. So the cost for that part, conquering part, 2 times T of 1/2 of the data size. But that partition, we need to pay this much cost. Although here I put big theta of n, but this is not a rigorous expression. We know the meaning, so actually we should replace this asymptotic notation here by some c times n. C, constant multiple. C, constant fixed. Constant c times data size n. Then we can do the computation a little better. Yeah. But here, big theta asymptotic notation just gives you the approximate idea we want to represent here. Yeah. All right, so next, solve this recurrence relation. How to solve it? How to solve it? Yeah. We did similar calculation before. Yeah. And here, if we solve it directly, that could be pretty hard. If we try to solve it mathematically, it could be pretty hard. Yeah. The reason is obvious. N over 2 may not be an integer, right? May not be an integer. So you may probably you want to replace it by floor function plus ceiling function, right? Something like this. Okay? In order to make the integer data size, you may like to do in that way. Then mathematical calculation could be very, very complicated. Yeah. So here, all right, here, let us use a technique we used before, recursion tree. Recursion tree method. It is much easier, much simpler than rigorous math computation, but it can give us a very good approximation. All right, so let's do it. Before we do it, first, we need to control how many recursions we need to go. That's important. How many levels of recursion we need to do. Yeah. So to do that, we try to find an integer k such that the data size n is between 2 adjacent power of 2. 2 to the kth and a 2 to the k plus 1. 2 adjacent power of 2. So we can do it, right? Yeah, any integer we can find such k. Yeah. Then we can, estimate that k. Yeah. All right. Because the reason we choose that k, if we do this calculation, you can see this is the data size after k iterations, right? K recursions. We do recursion k times. Then the data size is this. If data size is between 1/2 and 1, we should stop. So this condition tells us we should stop immediately. Or we call it termination condition. So this is the termination condition. Okay, so with that, then we can draw the recursion tree. Remember, when we draw here, we just accumulate non-recursion cost. So here, accumulate non-recursion cost. Yeah. Recursion part through recursions eventually disappear, right? Eventually, yeah, because at the end, at the bottom level, t of 1 equals 0. It's gone, right? Yeah, it's gone, no contribution. When you reach the very bottom level, right? Very bottom level, this t part, no contribution. So that's why we only accumulate non-recursion cost, C of n, Cn, C times n. Yeah, all right. So each level after accumulation, same Cn, right? Same Cn. Yeah. But how many levels do you have? Approximately k level, right? K approximately log of n. So then you do accumulation, simple accumulation, the total cost approximately big theta of n log n. Yeah. But that is the best case. So this is the best case. Okay, yeah, best case. All right. But, so this best case, we may like to know average case efficiency, right? Average case efficiency. Yeah. But the situation is too hard to estimate. Too hard to estimate average case efficiency. Yeah. Precisely. Okay? Yeah. Good, or with good approximation. So we do not do that. Yeah. So we just, take it still big theta of n log n. N log n. Yeah. We can do experiments, but it's very hard to give good estimate. Yeah. All right. So next, we like to go to the next, our last question. How to improve the performance. Yeah. Here, I just give you a few simple ideas. Yeah. First, randomization technique. Randomization. Remember, when we pick the pivot element, we do not favor any element in the given array. Right? Any element can be used as the pivot. Yeah. So here, although we use the last element as the pivot, so our textbook used the first one. Okay, our textbook used the first one. Yeah, equivalent. Yeah. All right, but sometimes that pick may not be good, right? Yeah, sometimes may have bias. Yeah, so we want to avoid that kind of bias. So the way we are doing random sampling. Random sampling. Yeah. That means we just select a random element in the array, swap it with the last element or the first element. Okay, yeah, depends on which partition version do you use. Yeah. After that swap, you have a very good chance to remove that bias. Yeah. Then we do the partition after that. Okay, yeah. There is another simple method that can help us improve the bottleneck worst case. Yeah, we try to improve the bottleneck worst case. That's called a median of 3 partition. So this time, we just do a little more work than this random technique. Random technique, very simple. Random, select one element, swap, then we are done. But this median of 3, we need to do a little more. Now, the result, it should be a little better regarding the partition part. The balance, the partition part, it should be a little better than the randomization technique. Yeah. But the median of 3, the overhead cost slightly higher than the randomization technique. You need to do a little more work. Yeah, that's the overhead part. Yeah. So we want to avoid extremal cases for the pivot. Yeah. So what do? We randomly select 3 elements in the array. So arbitrary 3 elements, randomly select 3, not 1. Then we find a median of these 3. Median of the 3 using 3 comparisons, right? So we know to find that we need 3 comparisons. That's the overhead part. So you'll pay this extra 3 more comparisons as the overhead. Then you expect to get a little better efficiency as the payback. Okay, so that's what you hope. Yeah. All right. So then you use that median as the pivot. Then you run the partition. Okay, yeah. Which one, it is not easy to say which one is better, which one is worse. Although we can do a project, do experiments on that. Yeah. For this semester, I do not assign that project. Yeah. I assign other, interesting projects. So I feel those projects will be more interesting than this one. Yeah. This one, pretty plain, right? And the result I can give you based on my experience before, yeah, because I assigned this project to my students before. Yeah. The result, with a little overhead, the occurrence of extremely unbalanced partition is greatly reduced. But when we do experiments, based on my impression, their performance almost the same. You need to pay more overhead. You get a little better performance. But if you put them together, the overall performance almost the same. Sometimes this one better, sometimes that one better, Yeah. And the original Quicksort may not be worse than these two, because these two pay more in the overhead part. So the original may not be worse. Okay, so that means these two, they can avoid the bottleneck. If you need to avoid bottleneck, then these two better. But if it's not that, if you only look at the overall performance, overall efficiency, the original one probably a little better. Yeah. All right, so that's the whole class for this Quicksort. Yeah. So let me complete whole video sequence here. Yeah.